Hello everyone, I am Ibrahim and today I will be presenting my project for CSCI E90 real-time environmental monitoring with AWS IoT and machine learning. This project leverages cloud technologies to build a scalable, cost-effective system for monitoring environmental conditions in real time. The objective of this project is to address the limitations of traditional monitoring systems which are often costly, inflexible, and lack real-time insights. By using AWS IoT and machine learning, we provide a dynamic solution for temperature and humidity anomaly detections. Our system simulates IoT devices streaming environmental data in real time. AWS Lambda processes the data, and Amazon SageMaker predicts anomalies. Alerts are sent through SNS, while data is archived in S3 for analysis. We also verified end-to-end data flow using AWS IoT Core and MQTT. Here is a high-level overview of our architecture. IoT Core manages incoming data streams. AWS Lambda processes the data, invokes SageMaker for anomaly predictions, and integrates with SNS for alerts and S3 for storage. SageMaker hosts a machine learning model for real-time predictions, and SNS sends notifications to stakeholders. The project followed a structured workflow. We simulated IoT data and pre-processed it for the model training by using SageMaker's linear learner model. We trained an anomaly detection model and deployed it. AWS Lambda integrates SageMaker predictions, detects anomalies, and sends alerts via SNS. Finally, we tested the system with various test events. Our project successfully identified anomalies in temperature and humidity conditions. The model achieved a robust performance matrix while processed data was securely stored in S3. Real-time alerts were delivered through SNS, and CloudWatch confirmed smooth integration across all of the components. So basically, the project demonstrates how cloud and machine learning technologies can address real-world challenges effectively. Actually, we faced challenges like limited data set size, model tuning for better accuracy, and managing cross-service permissions. Key lessons learned, including the importance of diverse data sets, continuous monitoring for real-time systems, and leveraging AWS services for scalability. Looking ahead, we aim to expand the dataset, explore new machine learning algorithms, and implement dynamic scaling for SageMaker endpoints. We also plan to extend the system to monitor another environmental matrix, such as air quality and energy usage. In the demo, I will demonstrate our real-time environmental monitoring system. First, I will present the Python script that simulates IoT devices streaming temperature and humidity data to AWS IoT Core. Next, I will take you into AWS IoT Core to verify the real-time data stream. Moving on, I will walk you through the AWS Lambda function, explaining how it processes the incoming data, invokes the SageMaker endpoint for anomaly detection, and securely stores the results in Amazon S3. I will also highlight the IAM role permissions that enable Lambda to interact with all of these surfaces. After that, I will demonstrate the Amazon SNS configuration, which sends real-time email notifications whenever anomalies are detected. We will then review the processed data stored in Amazon S3 for further analysis. I will briefly showcase the SageMaker Jupyter notebook used to train and to deploy the anomaly detection model. Once the setup is clear, I will run the Python script and we will observe the live data streaming into the MQTT test client. I will also show you the anomaly alerts arriving via email through SNS. Finally, I will wrap up by reviewing CloudWatch logs and metrics to confirm successful Lambda execution, SageMaker performance, and the overall system health. By the end of this demo, you will see how all AWS components work together to deliver real-time insights and notifications for environmental anomalies. Here is the Python file, and this Python script simulates IoT devices streaming real-time environmental data to AWS IoT Core. We configured the MQTT client with a unique client ID and secured the connection using AWS IoT credentials, including the root certificate, private key, and device certificate. Once connected to AWS IoT Core endpoint, the script enters a loop where it generates random temperature between 20 and 40 and humidity values between 30 and 70%. After that, formats the data as a JSON payload and pushes it to the MQTT topic every 5 seconds. Each published payload is printed to the terminal, simulating real-time sensor data streaming. This process allows us to mimic real-world IoT behavior and verify the data flow into AWS IoT Core. Now we will begin the demo in AWS, and as you can see here are all of the services that we have used throughout this project. And now I will walk you through the configuration in AWS IoT Core, where we set up our IoT device. We can go here to IoT, and after that, all devices, things. And here you can see the virtual IoT device named environmental sensor _1. We can click on it to see the details. And as you can see here, the IoT device has a unique ARN, which is Amazon Resource Name, and an active certificate attached to it. Here you can see it, yeah. Which enables, this certificate enables secure communication between the IoT device and AWS IoT Core. The certificate ensures that the only authorized devices can publish data into our core, IoT Core. You can also click on it to see its details. This certificate has been issued to the IoT device, and it is currently marked as an active, as you can see, and it is tied to a specific ARN and has an expiry date. And it ensures our device can securely interact with AWS IoT Core, as I said. We can see also that there is an attached policy to it. We can click on it. And as you can see here, the policy gives the following permissions. The first one is connect, which allows the device to connect to AWS IoT Core. The second one is publish, which enables the device to send data to a topic. The third one is subscribe, which allows the device to subscribe to a specific topic. And the last one is receive, which enables the device to receive messages from subscribed topics. And this policy ensures that the device can securely connect, publish temperature and humidity data, and receive messages as needed. And actually, these configurations are critical to ensure the secure and smooth connections between our Python script and AWS IoT Core. And now we can move forward and explore the next step, where AWS Lambda processes this incoming data. You can click on it. And here in functions, we can see our function, our Lambda function. Actually, this Lambda function is the core component of this pipeline. And here in the function overview, you can see the trigger from AWS IoT Core, which ensures that the data being published to the MQTT topic is passed to this Lambda for further processing. We can now explain the code of the Lambda actually. It's the whole code. Yeah. Actually, the Lambda function began with importing the needed libraries to interact with the AWS services, such as SNS and S3 and SageMaker. And actually, we have defined three constants for SageMaker endpoint name, SNS topic, ARN, and the S3 bucket, where processed the data will be stored in those constants. And actually, as we can see within the Lambda handler, the function extracts temperature and humidity from the incoming events payload. It prepares this data as a CSV formatted payload to send it to the SageMaker endpoint for predictions. SageMaker returns a prediction score, and the function check if this score exceeds a predefined anomaly threshold. And if an anomaly is detected, the function publish an alert to the Amazon SNS to notify stakeholders. Additionally, the function saves the processed data, including humidity, temperature, and the score, also the prediction score, as a JSON object in the S3 bucket to archive it for further analysis. Now, I think everything in the code is explained, so we can go to check here in the test tab. We can see some of our test event samples. We have 6 of them. Actually, you can see the JSON, which simply just contain a temperature and the humidity. We can go back to the code and try to run one of them. Okay. Yep. As you can see in the function output, the Lambda function successfully processed the IoT data. It logs the received event, prediction score, and anomaly detection message, and an SNS publish response confirms that a notification was triggered. And we can also see a confirmation that the processed data was successfully saved. This validates that our Lambda function integrates with IoT Core, SageMaker, SNS, and S3 to process and analyze real-time IoT data efficiently. I think that's everything here. And now I will show you the IAM role attached to our Lambda function, which enables it to interact securely with other AWS services. We can click on tools, and here we will be able to see our role for the Lambda, as you can see. And this will brings us the summary view, where we can see the key details, as you can see. The most important thing is the permission tab. you can see the policies attached to this role. The first policy is allow S3 put object, which provides the Lambda function with the permissions to store process data in our S3 bucket. The second one is a AWS Lambda basic execution rule, which allows Lambda to write logs to CloudWatch for monitoring and troubleshooting. The third one is invoke SageMaker endpoint policy, which gives the Lambda function the necessary permissions to invoke the SageMaker endpoint for anomaly detection. Finally, the SNS publish policy enables Lambda to publish notifications to SNS topic when an anomaly is detected. These permissions are critical because they enable our Lambda function to interact with those services, and without those specific permissions, the Lambda function would not be able to operate correctly within this architecture. So I think that's everything about it, and now I will demonstrate the SNS topic configuration that is responsible for sending the real-time anomaly notifications. I will navigate to SNS, and I can click on topics, and as you can see, we have a topic named anomaly notifications. I will click on it. This topic acts as the messaging hub where alerts are published when an anomaly is detected. And as you can see, here is the topic details, where you can see the ARN of the topic, and actually we can move on to the subscriptions tab, as it is the most important here. As you can see, there is one active subscription with the protocol set to email, and the endpoint set to my email, which will receive the anomaly notifications. For further clarity, I can click on it to see everything. This view shows the subscription details, including its confirmed status, the specific ARN for subscription, and the endpoint. And this confirms that the SNS topic is successfully configured and ready to send email notifications whenever an anomaly is detected. And actually, the setup ensures real-time alerts are delivered to stakeholders. And I think that's everything about SNS. And now I will demonstrate how the processed IoT data is stored in Amazon S3. I will navigate to S3. And under general buckets section, we can see our bucket listed, IoT process data 1. And I can click on it. And actually, this bucket serves as a repository for storing the output data processed by our Lambda function. And actually, it shows its contents, which includes a series of JSON files. And each file corresponds to a processed IoT data event that includes details like temperature, humidity, and also the prediction score, which is generated by the SageMaker model. And to confirm the data integrity, I will click on one of them and download it. I can open it. As we can see, its content. Here you can see the structure of the JSON that includes temperature and its value, which is 36.5, and humidity 75.2, and the prediction score, which is 41.30, and so on, and also the message process data from IoT device. And actually, this confirms that this data has been processed and validates that the Lambda function successfully saved the output in S3 after anomaly detection and processing. So now we move on to Amazon SageMaker, where the machine learning model for anomaly detection was built and deployed. I can navigate to it. And after that, click on Notebooks. And as you can see, here is our notebook instance, and its status is in service. And once I click on it, we can see its settings, like instance type and storage. And actually from here, I will open the Jupyter notebook, which contains all of the steps that we have made. And actually, to keep this demo focused and efficient, I will not go into the details of the code, but I will give you a brief overview about the important parts of the code and what we have accomplished in this notebook. And as you can see, we installed all of the required dependencies, including libraries like pandas and NumPy for data processing and sklearn for machine learning. And after that, the notebook retrieves the IAM role and set up the S3 bucket for storing input dataset and model artifacts, as you can see here. And after that, we generated an IoT dataset containing temperature and humidity, and this dataset was uploaded to S3 for processing. As you can see here, it is saved. And after that, the data was normalized using min-max scaler to scale values. And after that, that was followed by train test split of 80 to 20%, as you can see here. And actually, since the training and testing data set was uploaded successfully also to S3. And after that, since the SageMaker requires input data in record IO format, we converted the dataset and uploaded it back to S3, as you can see here. And after that, we configured the SageMaker linear learner algorithm, which is a regression model, as you can see here. And you can see it takes a little bit of time. And after that, the trained model was deployed as an endpoint for the real-time prediction, as you can see here. And we checked that it is already in service. And after that, we made some evaluations. As you can see from those inputs, we sent the test samples to the endpoint and calculated the error using mean squared error and mean absolute error, as you can see here. And after that, we visualized the comparison of predicted with the known labels using Matplotlib, as you can see here. And actually, we still have a lot of code, but we will not go through the rest of things. And as seen in this notebook, SageMaker simplified end-to-end machine learning workflow from training to deployment. And we now have a deployed model able to detecting anomalies in real-time IoT data, which integrates with the Lambda function that we have showed already before. So now I will run the Python script we discussed earlier, which streams real-time temperature and humidity data to AWS IoT Core. And once the script starts, it pushes sensor data every 5 seconds. And you can see the MQTT test client in AWS IoT Core that demonstrate the live data stream being received. Here you can see the incoming messages with the temperature and humidity values being published to the environment slash sensor one topic. And this actually confirms that the IoT device simulation is working as expected. I can just fill this close. And after that, let's check the SNS email notification triggered by anomalies. I will actually open the registered email inbox and see if I got some emails. Yeah, as you can see, I have just received emails about those notifications. And these messages includes, as you can see, details such as the temperature, humidity, and the prediction score. And finally, I think we can show also the process data, which is stored in Amazon S3. Let me navigate to S3. Let's check our bucket here. And let's see the last JSON file. You can download it and open here, which is the last one, as we see, and the prediction score and the message, which is this one. And if we check the other files, we will show the previous messages. So finally, I will showcase the CloudWatch logs and matrix to confirm that all of the components of our system are working. First, I will navigate to logs and log groups, and I will open the logs generated by process IoT data, which is our Lambda function. And here you can see detailed logs, including the received IoT data, the SIGMaker prediction results, SNS publish confirmation, and the status of data storage in S3. All of those are logs. We can check one of them. Here you can see received event, temperature, humidity, SIGMaker prediction score, anomaly detected, SNS publish, data stored in S3, and request, and so on. So after that, I think that I'm going to switch to CloudWatch matrix, all matrix, and here we can see that we have a lot of them, but we are going to focus on the Lambda. And as you can see, there is no alerts at all. And in Cloud Watch Matrix, in this Cloud Matrix, we can monitor the system performance and matrix for Lambda execution and errors, which help us understand the efficiency of the function and identify any bottlenecks. And by combining CloudWatch logs and matrix, we can validate the overall health and performance of the system. And this actually confirms that data is flowing from IoT Core, Lambda, SIGMaker, SNS, and S3, ensuring the entire pipeline is efficient. So this concludes the demo, and we have successfully showcase the system, and the system is modular and scalable, and it can be adapted for various IoT and machine learning use cases. Thank you very much for your time, and I am very happy to answer any questions.